Problem 3. Two radio antennas radiating in phase are located at points A and B 200 meters apart. The radio waves have a frequency of 5.8 times 10 to the 6 Hertz. A. At what distance from B will there be the first destructive interference location along the BC line? B. What is the relative intensity at the point x equals to 100 meters from point B? I. If this point is closer to a dark or bright fringe, what is the fringe number? If not, is it closer to a dark or bright fringe? Draw a sketch of the interference pattern and show where this location x is located. First step is to determine the interference pattern by calculating the interference parameter, d over lambda. The wavelength of the radio antenna is given by c equals lambda times frequency. So lambda, when you plug in the speed of light, gives you 51.7 meters. Then the diffraction parameter, d over lambda, is in 3.87 to 3 sig figs. In the path difference equation, delta r is d sine theta, which is equal to mc lambda. My mc maximum value is the diffraction parameter, which is 3.87. What does this value mean? mc equals to 0 implies that the path difference must be 0. The only way this could be true is if you're at infinity. If mc is equal to 3, that means that there are 3 bright fringes. That is mc1, mc2, mc3. But when I look at 3.87, this m value of 0.87, I know that m equal to a half integer is related to a dark fringe, where any whole integers a bright fringe. So you could see here that 0.87 is going to be closer to a bright fringe than it is a dark fringe. And what you're seeing here is that it's not at maximum intensity. So it's closer to a bright fringe than a dark fringe. Sketching the interference pattern, at mc equal to 0, we know that's at infinity. Then I got 3 brights, full brights. So I get 1, 2, 3. And then I got mc equals to 387, but that's not at all the way up. So then if I look at md, then I could see that that's got to be 0, 1, 2, 3. So if I look at the number of dark fringes, turns out that I see 4 of them. How many brights do I see? I see 1, 2, 3, 4, and then I get a partial max. I'm going to get 4 maximal bright fringes, 0, which is 1, 2, 3, 4. I get 1 partial bright fringe, which is at 3.87, and I get 4 dark fringes, 1, 2, 3, 4. What location will the first dark fringe appear from source B? We could see here that it's got to be MD equal to 3. Picture-wise, I have A, B, and C. A travels farther than B by the path difference delta R. So if I want to calculate what that value is, I know that this occurs at MD equals to 3, so then I write MD equal to 3. I know that this angle here must be theta of 3. So now I have a full triangle. I can calculate the angle using this relationship, and if I know the side D, I can then calculate this length along the BC line. Once again, I calculate theta 3 from the path difference equation. Once I have that, I then solve the triangle for x3. I know what D is, I know what theta 3 is, so now I can solve for x3, the distance that's to the first minima from source B. Path difference equation gives dr equal to d sine theta 3, which is equal to 3, md equal to 3 plus 1/2 times lambda. Solving for theta 3, I then get that I get the sine inverse of 3.5 divided by the diffraction parameter at an angle of 64.7 degrees. From the triangle, I get that d divided by x3 equals the tan of theta 3. So x3 is equal to d divided by tan theta 3, which then gives me a value of 94.5 meters. So this is how far minima MD equal to 3 is located.